Good afternoon, everyone. Welcome. Today our speaker is Naci Saldi. Naci Saldi received his BSc and MS degrees from Electrical Engineering and Electronics Department from Bilkent University in 2008 and 2010. He received his PhD degree from the Department of Mathematics and Statistics from Queen's University. After that, he was a postdoctoral scholar at IEEE. Then he joined Ozyegin University's Department of Natural and Mathematical Sciences. He is the co-author of the book Finite Approximations in Discrete Time Stochastic Control, published by Springer. His research interests include stochastic and decentralized control, source coding, mean field games, and applied probability. Now, we'll listen to Naci.
Thank you for the introduction, and thank you for the invitation. I'm very happy to be here at Electrical Engineering Department. So today I will talk about decentralized control, and in particular we will see approximations of decentralized control problems, and this is a joint work with my colleagues Can Deha, Maxim Rajitsky, and Eric Ambar. Okay? And the outline of my talk is as follows. So I will first give a general overview of decentralized stochastic control problems. In particular, I will talk about the difference between classical stochastic control problems and the decentralized version of stochastic control problems. And we will see a very important example, decentralized stochastic control example, which is called the Witzenhausen's counterexample. So this problem is very simple to state, but it is still an open problem in decentralized control theory, and it actually demonstrates the difficulties arising in decentralized stochastic control. And then I will introduce two relaxations to the classical decentralized stochastic control policies. The first relaxation is the randomized policies, and the second relaxation is non-signaling policies. And using non-signaling relaxation, we will then obtain an approximation result for decentralized control problems. Okay? So, stochastic control theory considers control and optimization of dynamical systems in the presence of stochastic uncertainty. Okay? In classical setup, we have a single agent. Okay? This agent has some stochastic dynamics, and depending on the observation the agent gets from the system, it designs its controls. Okay? And the goal is to minimize some cost function. Okay? So in classical stochastic control setup, all the available information in the system is collected in one centralized unit. Okay? So it gets all the information available and designs the control, and the goal is to minimize the cost function. But in the centralized setup, okay, instead of a single agent, we have number of agents, and these agents have different information about the system, and their goal is to collectively minimize a cost function. Okay? But in the centralized setup, they are not allowed to communicate with each other. Okay? Okay? And since in the centralized setup you cannot collect all the available information to one centralized unit, the problem is much difficult than the classical version. Okay? And some applications areas of decentralized stochastic control are as follows. So you can apply the findings to network communication systems. So here you have a number of encoders and decoders, and they try to communicate over noisy channels, and their goal is to minimize the distortion in the message. Okay? Or you can apply decentralized control theory to smart grid systems. So you have multiple electricity suppliers, and they act together using their local information to coordinate electric supply and demand effectively. Okay? Or you can apply decentralized control theory to transportation networks. So in this case, you have vehicles, and they try to prevent traffic congestion. Okay? And they can do this by using their local information obtained via navigation or smart driver assistants. Okay, so they have to design their controls using their local information to collectively prevent traffic congestion. Or you can apply decentralized control to robot control, or you can apply decentralized control theory to economic networks. Okay, so it will, the application areas will continue like that. Okay, so it's a very important area right now in control theory. Okay, and in decentralized control theory, information structures, okay, specify which agents know what, okay, the information available to the agent, and also it specifies the impacts of decisions of agents on another agent's information. Okay, therefore, in decentralized control, okay, the actions of agents affect the observations of other agents. Okay. And the challenge in the decentralized system is the decentralized and asymmetric nature of the information structure. So suppose you have two agents, okay, so they have different information about the system. So this is the decentralized nature of the problem. And also, for instance, agent 2 can affect the observation of agent 1. Okay, although it cannot observe the observation of agent 1, this is the asymmetric nature of the information structure. Because of this decentralized and asymmetric nature, okay, finding the optimal policy and the optimal cost function is quite difficult. And indeed, we can prove that finding optimal strategy or policy is proved to be NP hard. Okay? And because of the decentralized nature, you cannot apply the classical solution methods in classical stochastic control theory like dynamic programming, value iteration, policy iteration, linear programming, or convex analytic methods. Okay? And indeed, people realize that decentralized control problems are difficult than the classical stochastic control problems after Witsenhausen formulated this famous counterexample. Before Witsenhausen's counterexample, people believed that, okay, if you have a linear system, if the primitive random variables are Gaussian, and if you want to minimize a quadratic cost function, even if you have a decentralized system, then the optimal policy must be linear. Okay? So in stochastic control theory, we know that if we have a linear system with a Gaussian noise, if you want to minimize quadratic cost function, then you can prove that the optimal policy should be linear using Kalman filtering method. Okay? But Witsenhausen constructed this decentralized system, and as you can see, okay, the system is linear. Okay, mu0 and mu1 are controllers for agent 1 and agent 2. System is linear. Okay, all random noise and the initial distribution are Gaussian. Okay, and you want to minimize the following quadratic cost function. Therefore, we have a decentralized linear system with Gaussian noise, and you want to minimize a quadratic cost function. But Witsenhausen proved that, proved that the optimal policy should be nonlinear. Okay, how did he do the proof? Okay, he constructed the following simple policy for agent 1. Okay, so here he did the following: if y0 is positive, okay, he mapped y0 to a fixed positive number. And if y0 is negative, then he mapped this y0 to a fixed negative number. In other words, he quantized y0 using two-level quantizer. Okay? By applying this simple policy, he proved that the optimal cost function that you can obtain by applying this simple policy is much bigger than the optimal value function or cost function that you can obtain using linear policies. Therefore, he concluded that optimal policy should be nonlinear. Okay? And after this result, he proved the existence of optimal policy. He proved that there should be an optimal policy, but he couldn't find the optimal cost function, as well as he couldn't find the optimal policy. And still, these are open problems in control theory. Okay? So this problem is very simple. Okay? but we still don't know the optimal policy and the optimal cost function. Okay? This actually shows how difficult the decentralized control problems compared to classical stochastic control problems. Okay? Okay. So I think we all understood how centralized stochastic control problems can be difficult. Okay. Now I will formulate the problem. Okay. Centralized control problem. To formulate the centralized control problems, I will use the Singular's intrinsic model. Okay. So this model actually captures every sequential decentralized stochastic control problem. So if you have a system where there's a prescribed order of actions, so for instance, first agent 1 acts, then agent 2, then agent 3. If you have such a system, then you can always transform your model into this, with another intrinsic model. So this is a very general model to use, okay, in order to model decentralized control problems. So in this model, we have n agents, okay. We have a state space X, okay. For each agent I have action space AI and observation space Y. Okay? And probability measure mu is probability measure mu is defined on state space X, and it describes the uncertainty on the state variable X. Okay? Little x is the state variable, mu describes the uncertainty on this variable. Okay? And for each agent I, we have an observation variable yi, okay? And this yi has the following conditional distribution, so wi is indeed an observation channel, and given state variable x and the previous actions, okay, applied by previous agents, the distribution of yi is given by this observation channel. Okay? Therefore, the actions of other agents affect the observation of agent I in the system. And based on this observation yi, agent I, okay, should design its action. So AI is the action of agent I. It is indeed a function of yi. Okay, so gamma I here represents the policy of agent I, and it should be a function from observation to the action. So this is a deterministic function. So we don't have any randomness when we are designing in our actions. Okay? So therefore, agents can only use their local observation yi when they are designing their control actions. Okay? And what's the problem? The problem is the following. So by designing this joint policy gamma, agents try to minimize the following cost function. So here C is a cost function, and it's a function of state, all observations, all actions. Okay? And since we have a stochastic system, we have to minimize its expectation. Therefore, by designing this joint policy, we want to minimize this expectation. In other words, we want to find a joint policy gamma star, okay, such that it minimizes this cost function. And of course, this gamma star here, this joint policy, should obey this information structure. Okay, so gamma I star here should use the observation available to agent I, which is yi. Okay. So this is the control problem. Okay, and people it's proved that computing the value of optimal value of this function J star. So remember, J star is the optimal value. So computing this value is proved to be NP hard. Therefore, computing the optimal policy is also very hard. And therefore, since this is difficult to compute, you need to approximate the problem in order to obtain approximately optimal policies, or approximately compute the optimal value J star. Okay? And in this work, in order to obtain approximate value for J star, okay, I introduced two relaxed versions of classical policies. Okay? So in classical policies, what we have, agent I observes something, yi, and deterministically designs its control ai. Okay? So in randomized policies, okay, as we will see, agents can randomly pick their actions. And in non-signaling policy, we have the non-signaling condition that I will explain in the future. Okay? And after this relaxed versions of classical decentralized policies, I will obtain a linear programming approximation, okay, based on the non-signaling policies and plus some symmetry. Okay? So this is the idea. So I will first introduce these relaxed policies, and then we will obtain our approximation result. And before I will do that, let me simplify my problem. So I think I forgot to tell you, in this problem I'm assuming that the state space, the observation spaces, and the action spaces are finite. Okay? So they are not abstract spaces, they are all finite spaces. If this is the case, then you can actually transform your problem into a simpler one. So for any fixed choice of a joint policy, the corresponding cost function can be written like that. And if I incorporate observation channels and the distribution of state into the cost function, then I can equivalently write this cost as follows, where capital C is just a function of observations and actions given by this expression. As you can see, I incorporated observation channels as well as the distribution of the state into the cost function, and pi generates the observation, and observations are generated independently because we have a product structure here, and they are generated uniformly over the space that they are living in. Okay? So this is actually called static reduction of our problem. Therefore, my cost only depends on observations and actions, and observations are generated independently and uniformly. Okay? Now, using this static reduction, I will now introduce randomized policies. So note that we can view any policy as a conditional distribution on actions, all actions given all its observations, but of course it should satisfy some condition. In other words, the distribution of AI should only depend on yi. Okay? So, in other words, we can view any policy, any joint policy, as a conditional distribution of all actions given all observations. Okay? And using this view, we can now introduce randomized policies. So randomized policies are conditional probabilities on all actions given all observations with the following structure. Okay? So in the classical case, okay, AI is just a function of yi, but in randomized policies, AI is a random function of the observation yi, as well as this extra randomization omega, which is called the independent common randomness. So this randomization can be used by all agents, but this omega is independent of the system. Okay? So in randomized policies, agents can use its observation, its observation, as well as this common randomness, and also they can randomly map this information to the action space. Okay? They can also use individual randomization as well, and this set is the set of randomized policies. Okay? So what do we know about randomized policies? First of all, the conditional distributions on actions given observations induced by classical deterministic policies, okay, is not convex. Okay? But if you use randomized policies, you can prove that the set of randomized policies, okay, is a convex set, and the extreme points of these randomized policies are the deterministic policies that we have at the beginning. Okay? Therefore, if you want to minimize the cost function using randomized policies, the optimal value will be equal to the optimal value that you will obtain at the beginning, because the cost function j is indeed a linear function of the policy. Since it's a linear function, it should take its optimal value on extreme points. Therefore, these two quantities are the same. And since the extreme points are the deterministic policies, then common and individual randomization does not improve the cost function. And since we have to search for the optimal policy over these deterministic policies, then computing the optimal value for randomized policies is still MPT. So this relaxation, it doesn't give anything to us. So we still have the same problem. We have to search for the optimal policy over the set of deterministic policies. So this is not helpful. Now I will introduce another relaxation, which is called the non-singular relaxation. This is stronger than randomized policies. The definition is as follows. So a policy, now remember I'm considering policy as a conditional distribution of actions given observations. So this conditional distribution is non-signaling F for any subset of agents. The actions of agents in this subset, given all the observations, if the actions of agents in this subset, given the observations, are independent of the observations of agents not in this subset, then this conditional distribution is non-signaling. In other words, you have to have the following conditions. So probability of actions AK1 to AKM given all observations is equal to probability of AK1 to AKM given only the observations corresponding to these agents, then your conditional distribution is non-signaling. And we can prove that the set of non-signaling, the extreme points of set of non-signaling policies is bigger than the set of deterministic policies. Therefore, this set is bigger than the set of randomized policies. And we can characterize non-signaling policies using the following condition. So this condition says the following: the conditional distribution on actions, conditional distribution of actions given all observations is non-signaling if and only if for each k, the conditional distribution of actions excluding AK is independent of the observation yk. In other words, you have to have this condition for all these variables. And as you can realize, this condition 1 is a linear condition on conditional probability. And the number of such linear condition is this number. Therefore, since we have a linear condition in non-signaling case on the conditional probability, I can write the optimization problem corresponding to the non-signaling policies as a linear program like that. So remember, this was my cost function. This is the distribution of observations. So I need to design this to minimize this cost. And this conditional distribution should satisfy the following conditions. So these two conditions ensures that this P is indeed a conditional distribution. These are linear constraints. And also in non-signaling case, P should satisfy the condition that I introduced here. And this is also a linear constraint. Therefore, I can write my optimization problem as a linear program, and I can easily solve this optimization problem. So this is the second relaxation. Therefore, and in particular, I can prove the following: the optimal value of the non-signaling policies is strictly less than the optimal value of randomized policies. Okay, and I can write this optimization problem as a linear program. Therefore, I can quickly solve this problem. I can find its optimal value. Okay, that's good. But we have a problem. Okay, when you find the optimal value, optimal policy of this, okay, problem, sometimes to implement this optimal non-signaling policy, agents need to communicate with a centralized unit. Okay? So agents should send their information to some centralized unit, then centralized unit will do some operation on these observations and dictates agents to apply certain, okay, policy. And this is in general prohibited in decentralized control. Therefore, although we have a nice relaxation, non-signaling relaxation, okay, the policies sometimes, okay, cannot be implementable in decentralized setting. Okay. And actually, one such problem is CHSH problem that I will introduce now. So in this problem, we have two agents, okay, and observation and action spaces are binary spaces, okay, and observations are generated independently and uniformly. So in this problem, we want to maximize a reward function. Okay, so you can actually apply any findings that we have here for minimizing cost function to maximizing a reward function. Okay, so here we want to maximize a reward function for given observations and actions. The reward function has the following structure. So given y1, y2, a1, a2. Okay. You will get reward of 1 if the binary sum of a1 and a2 is equal to the product of the observations, y1, y2. Okay? And you will get reward of -1 otherwise. Okay? Okay? And in this problem, we can show that randomized policies can achieve the maximum reward of 0.5. Okay? However, if you allow non-signaling policies, then the non-signaling policies can achieve the maximum possible reward of 1. Okay? And the policy that you need to apply in non-signaling case is the following. Okay? So if the conditional distribution of a1, a2 given y1, y2 is 1/2 if the binary sum of a1 and a2 is equal to a product of y1, y2. Okay? If this is not the case, then you will give the 0 probability. Okay? And if you apply this policy, you can easily see that by this cost structure, you will always get the reward of 1, okay, for all realization. Therefore, the total reward that you will get is 1. Okay? And you can actually prove that this policy here, the conditional distribution, okay, obeys the non-signaling condition. Okay? However, although okay, this okay, achieves the maximum reward, and you can find this policy using by solving the corresponding linear program. In order to be able to okay, implement this policy, you need to do the following. Okay? So first, agents, when they observe their observations, y1, y2, they should send these observations to a centralized unit. Okay? Centralized unit, okay, computes this product y1 times y2. If this product is 0, then centralized unit dictates the agents to apply the same action. Okay? Sorry, if the product is 0, then centralized unit dictates to agents to apply different actions. Sorry, same action, sorry. Okay? If this product is 1, then centralized agents dictates agents to apply okay, the same policy. Okay? Therefore, in order to be able to implement this policy, okay, there should be a communication between agents and a centralized unit, and this is in general prohibited in the centralized stochastic control theory. Therefore, you cannot implement such okay, policy in decentralized control. And this indeed shows that non-signaling relaxation is not legitimate in the centralized control theory. So in summary, what we have, okay, we know that computing the optimal value function of decentralized control problems is NP hard. So we need to approximate these models, okay? So we introduced two relaxation, randomized policies and non-signaling policies, okay? And finding the optimal value for randomized policies is still NP hard. For non-signaling policies, we can find the optimal value and optimal policy using linear programming formulation. Okay, this is good, but in order to implement optimal non-signaling policies, you may need to, okay, you may need to allow agents to communicate with centralized unit, which is not possible in the centralized system. Okay. So far we have this. Now, what I will do now, I will introduce another set of policies. These policies are called extendable non-signaling policies. So these policies are between randomized one, okay, and the non-signaling modes. Okay? And we have a parameter, k, which is indeed a vector that contains, okay, integers. Okay? By actually varying this parameter, I can actually I can control the distance between the extendable non-signaling policies and randomized policies, and the distance between extendable non-signaling policies and non-signaling policies. So I can move between randomized and non-signaling policies by actually controlling this variable. Okay. So given this vector k, where k1 to kn are, okay, positive integers, then k extendable non-signaling policies is defined as follows. So a policy which is a conditional distribution on actions given observations is k extendable non-signaling if we can find p tilde. So p tilde is the extended version of p. It's a conditional distribution on k1 times on k1 copies of the action space of agent 1, k2 copies of action space of agent 2, and kn copies of action space of agent n. Okay, so we are actually adding auxiliary sets here. So p tilde is a conditional distribution on this set, on these spaces given, again, the extended observation spaces. This p tilde should be non-signaling, okay? It should be symmetric, and also the marginal of p tilde should be my original policy. Okay? So if we can find such an extension to p, then we say that p is k extendable. Okay? And I can prove that this set is a subset of non-signaling policies. Okay? And I can also control this variable. When I control this variable, and the first important result says that, okay, the distance between randomized policies and k extendable policies is not big if you have enough extension. Okay? So if these numbers k1 to kn are large enough, then the set of randomized policies, the distance between the randomized policies and the distance between k extendable policies, okay, is not big. Okay? So this is the first main result. Okay, why these policies are important? Because I will now, using k extendable policies, I will introduce another problem. Okay? So in this problem, okay, what I will do, I will add extra identical agents to the model. Okay? So what I will do, for agent I, okay, I will add ki minus more agents that are identical to agent I. Okay? So for instance, so this is agent I, okay, agent I, and I will add ki identical agents like that. Okay? So I will do this for all agents. Okay? Therefore, in the extended problem, we have K1 plus K2 plus K3 plus up to Kn agents. Okay, the number of agents are now bigger than the original problem. And what I will do in this extended game problem, I will generate the observations, which are the observations in the original problem, so y1 to yn. Then I will send the observation, the ith observation yn, okay, to the one of the ki agents chosen at random. Okay, so we have ki agents. Okay, I will choose one of them randomly and send yi one of them. Okay, and I will do this for all I. Okay, and if I don't send any observation to the agent, then I will not expect anything from this agent. Okay, and then using actions and observations of the chosen agents, okay, I will compute the cost function that I have at the beginning. Okay, and I will not expect anything, okay, from the agents that I didn't send any observation. Okay, so this is the extended game. So in extended game we have K1 plus K2 plus Kn agents. Okay, we have a bigger observation and action spaces. But what I can prove the following: the optimal value of non-signaling policies for this extended problem is actually equal to the optimization of my original problem over the K extendable non-signaling policy. Okay? But what I know about optimal value of non-signaling policies, I can find this optimal value for the extended problem using linear programming formulation. And the linear programming formulation for the extended problem scales with this number. Okay? This is good, so I can compute this using the linear programming formulation of non-signaling policies of extended problem. Okay? And I also note that I can approximate any K-extendable policy using randomized policies. Okay? And using these two observations, I can prove the following. Okay? For the original decentralized control problem, okay, I can find a linear programming approximation. The size of this linear programming approximation scales with this number for computing J star, and the error that I will get is this. Okay? So this is indeed the first approximation result with an explicit, okay, error in decentralized control literature. Okay, so this is the first result, but this error here is not that good because it scales exponentially with the cardinality of action spaces. So if the cardinality of your action spaces are, for instance, 5, and if you want the very precise value for J star, for instance, if you want error to be 0.001, then the size of the approximation, the size of the linear programming approximation will be very huge. Okay? But if you want to find the half of the optimal value, okay, the half of the optimal value, then the scale will be not big. Or if you want to find, 1/10 of the optimal value, again, you will get a reasonable linear programming approximation. Okay? Okay? But however, if you want epsilon to be very small, then this approximation will be very huge, and it's not possible to solve this linear programming problem. Okay? Good. So this is the main result, and this is the first result in decentralized control with an explicit error bond, although we don't have a good error bond here. So in conclusion, in this talk I introduced two relaxed versions of classical policies, decentralized policies. The first relaxation is the randomized policies, and the second relaxation is non-signaling policies. I talked about their advantages and disadvantages. Okay, In particular, I can write the optimization problem corresponding to non-signaling policies as linear program. Therefore, I can easily find its optimal value. However, to implement the optimal policy for non-signaling policies, you need to allow agents to communicate with a centralized unit, which is not possible in centralized theory, control theory. Okay, and using non-signaling policies, we then obtain approximation of decentralized control problems by adding extra structure to non-signaling policies like extendability. And actually we can control the approximation using the variable that we introduced for extendable non-signaling policies. Actually, in the original work, I also introduced quantum correlated policies. So in quantum correlated policies, we are allowing agents to implement some quantum operations. Therefore, they can use the power of entanglement to correlate their actions. And quantum correlated policies are between randomized policies and non-signaling policies. And the good thing for quantum correlated policies is that agents do not need to communicate with each other or with a centralized unit. Okay? So they can do this operation decentralizedly. However, actually this is an open problem. We don't know whether we can write the optimization problem corresponding to quantum correlated policies as a linear program or as a semi-definite program or some mathematical program. Okay, so this is indeed an open problem. I'm still working on this. Okay, and finally, so here we obtain this error bound by adding artificial symmetrization to the problem. Okay, so here we add identical agents, and this identical agents lead to some symmetrization in the problem. So in order to improve this bond, what we can do, we can assume some symmetry structure in the original problem. Okay? So if we assume that the problem is symmetric in some sense, probably we can improve this bond. Okay? Can improve this bond. And another important, actually interesting problem is by adding symmetry here, so by increasing k, actually we are adding artificial symmetry to the problem, and as k goes to infinity, or in other words, when k goes to infinity, of course the number of agents will go to infinity in the problem. So by adding this extra symmetry, then the difference between randomized policies and non-signaling policies will vanish. Okay. Another interesting problem is the following. So suppose you have a problem with infinitely many agents and your problem is symmetric. So in this case, can you prove that non-signaling policies are the same with the randomized policies? Okay? So if this is the case, then in the infinite population limit, you can easily find the optimal policy and the optimal value function using the linear programming formulation of the problem. Okay, so this is another direction that I am working on right now. I think I'm done. Thank you for listening. Okay, if you have any questions, I'm very happy to answer.